Okay, you should have watched already the lecture on the problem of induction, and you have attended the Zoom lecture or discussion really on Monday. So now this is for Wednesday, and this is on Karl Popper and falsification. So this is one sort of solution to the problem of induction. But he starts us off by sort of explaining once again the problem of induction. Important. So once again, the traditional view is that scientific method is inductive, right? We go from singular statements, singular observations, to universal statements. And the way you do that is to use inductive logic. So the argument is something like we observe the same thing over and over occurring, or a similar thing over and over. Let's say that swan 1 is white. We see a swan, it's white. We see another swan, that swan is white. We observe 200 swans, 1,000 swans, 1,000,000 swans. The number doesn't really matter so much, right? But after some number of swans, right, which is sort of indeterminate, we haven't figured out exactly what is the right number of swans that you have to observe. But at some point, you conclude, okay, all swans are white, right? So it's inductive because the conclusion says more than the premises did, right? The premises only note a certain number of white swans, and the premise makes this general claim, all swans are white, right? So we can use that to make predictions, right? If you say you have a swan at home in your backyard, before even looking at it, I know it's white, right? If I know the claim, all swans are white, is true. But the problem we saw with Hume, right, is what justifies that leap, right? Because given the premises that we started with, it's always possible the conclusion could be false. There might have been a black swan out there and we just didn't observe it, right? Maybe it was swan 201. So that is the problem of induction in a nutshell, right? No matter how many white swans I observe, there might be one that isn't white. And so that makes our claim, our conclusion false, or potentially false. So here's another way, yet another way to talk about the problem of induction. Are inferences to universal statements, like all swans are white, can they be valid based only on experience, right? Is there any way that, and again, this is important because this is how science operates, right? We observe, right, which is a kind of experience, and we draw general conclusions. So the question is, could that ever be a valid form of reasoning, right? Could I ever infer that all swans are white based on my swan experiences? As we've seen, all experiences are singular, right? There's no general experiences. I don't experience all swans at any point, right? I only see one swan or maybe a finite group of swans. I don't ever see infinite numbers of swans. And so we're trying to get to a universal claim, but our evidence is just not universal. We just don't have infinite experiences. So the question is, maybe we could have some sort of rule that would allow the inference, just like we have modus ponens, right? Which just allows us to say, well, if A, then B, and A, therefore B, right? Maybe there's sort of some kind of rule, some sort of principle of induction that would justify going from 200 swans are white, therefore all swans are white. So yeah, the principle of induction, if such a thing existed, would say something like, if 1,000 Fs are observed to be Gs, right? And these Fs and Gs, you'll run into this a lot, right? And that's just sort of like stands for any arbitrary property that something might have. So 1,000 things are observed to be swans, and they're also observed to be white, right? So F being is a swan and G being is white. You can conclude that all Fs are Gs, right? Yeah, so just plug in the thing of interest for F and G. Here it's swan for F, and I should have said white for G, sorry. So we're back to our old problem, right? Why should anybody believe the principle of induction, right? So that's, I guess, if you had that principle, right, if you thought that was true, then that would justify inductive inferences. But the question is, where does this principle of induction come from? What good is it, right? Is it actually reliable? And this is, similar, basically another way of saying what Hume was worrying about. Well, what kind of statement is it? It's not an analytic statement, right? It's not true in virtue of meaning, right? So statements like all bachelors are unmarried, we know that's true just by looking at it if we know what bachelor means and what unmarried means, right? Because bachelor means unmarried man. So it's contained in the concept of bachelor that they're unmarried. So we don't even have to go around and survey bachelors and ask them if they're married or not. We know just from the meanings of the words that that is true. So that's an analytic statement. That's analytically true. But all swans are white is not an analytic statement, right? And nor is the principle of induction an analytic statement. It is not true just in virtue of the meanings of the words that if you observe something 1,000 times, then the 1,001st will be the same, right? There's nothing in the meanings of the concepts included in there that makes that obviously true. And then, like Hume said, Hume's test was, well, does it sound contradictory? And it doesn't, right? So it's not analytic, so it must be synthetic, right? It's a statement whose negation is not contradictory. It's totally possible that you could observe 1,000 white swans and yet there's a black swan out there. And so it would be false. All swans are white. So having stated sort of the problem of induction once more, Popper talks a little bit about some of the solutions or things people have said in reply. And if you read the Stanford Encyclopedia article, you may have seen a few of these. I think some of these may be additional ones that aren't in there. But there's lots of things people have said to try to show that the Hume's argument is not sound, right? That induction can be reliable. So Reichenbach's point is that, look, we all just believe it, right? Humans use it all the time, so do scientists, right? I don't go around, if I eat, well, like our example of Zig, right? In real life, if I eat one horseradish donut, maybe two or three, I'm going to conclude that they suck, and I'm not going to keep eating them. Right? That's just like a basic component of our nature, of the way we reason in the world, right? And Hume, was asking, well, can you justify it? And Reichenbach's saying, I don't know if I can justify it, but we can't do without it, right? So, right, let's just go with it. And science uses the same thing. It's just a basic human thing, right? So, just like horseradish donuts, I don't have to touch fire over and over and over to decide that it's hot, right? That all fire is going to be hot. And we saw the example with Newton, right? He tried it a few times in a few different configurations, tried to rule out some sources of error, but he didn't go around trying it every day and saying, well, I wonder if right, light rays are going to diffract at different angles. The components of a light ray are going to diffract at different angles on today, but not tomorrow, or tomorrow and not yesterday, or maybe it's on Fridays but not Wednesdays, or maybe every second Friday of every third year, right? He's not worried about that stuff. But this sort of line of argument doesn't really convince Popper, because it may be true that that's just how everyone reasons and that's how humans operate and that's how our brains work, but it doesn't mean it's a good way to reason, right? So it's just because everyone believes that there is some sort of principal induction that we can reliably follow, that doesn't mean that it is actually reliable, right? Maybe everyone's just wrong. Just like Hume says, give me a reason, right? Don't just tell me that we do it. Then Popper describes Kant's reaction to this problem of induction, right? So Kant thinks that there is a principle of induction, but it's synthetic a priori. So we can't go too deep into Kant. It's pretty confusing stuff sometimes. But in short, right, my two-sentence account of Kant is, Kant thinks that to be a human and have the sort of experience that humans have, there are like certain preconditions that have to be there, right? For example, our experience is always in space and in time, right? We don't have experiences that aren't temporal. We might actually have experiences that aren't spatial, right? Just, if you close your eyes and just think about stuff, right? Then that doesn't have to be spatial. Everything's definitely in time, and most of our experience is spatial as well, right? And he says that's just the form of our experience, but it's not a necessary thing, right? It's not it's synthetic, right? It's not analytic. There's nothing about the meaning of the word experience that means that it would have to be in space and time, but that's just how it is for us. So maybe the principle of induction is kind of one of those things, right? So human experience is just going to follow the principle of induction, just like it's always going to be spatial and temporal. That's sort of the best quick gloss I can give on Kant. If you're interested in this, you can read more on it. Again, and I'm not going to get into why Popper doesn't think that's a good idea, but he mentioned it in his paper and he didn't really spend any time. So if you read that, I wanted to try to explain it a little more. Okay, so here's another way you could maybe try to deal with induction. Maybe you say, oh, when we conclude that all swans are white, right, from having observed 1,000 swans, you might say, sort of in parentheses before that is a little probably, right? Probably all swans are white, right? So maybe you think that when we do inductive inferences, that's the sort of conclusion we get, right? It's a probabilistic conclusion. And so the principle of induction would be something like, if you observe 1,000 F's and G's, then probably all F's are G's. But once again, Popper thinks, well, this doesn't solve the problem, right? Because observing 1,000 swans doesn't even actually prove that swans are probably white, right? Especially if there's millions of swans up there. Maybe there are there are 999,000 black swans, and I just happen to observe the 1,000 white swans, right? So switching to a probabilistic conclusion doesn't seem to help very much. And we just run into the same thing, right? Anytime we try to come up with a principle of induction, and then you're asked to justify that principle, even a probabilistic version, you kind of end up with a circular argument, like we've seen over and over in Hume and the Staley version of Hume. So Popper just gives up on induction. He says, look, there's no way we can rationally justify it, and we should try to think about science in another way. Sorry, I keep wanting to get into the video. Popper offers an analysis of the scientific method as deductive, right? Not inductive. Deductive reasoning, we don't really have any problem with, so long as you believe, rules like modus ponens, which everyone seems to think are sort of more secure than inductive inferences. So he proposes a deductive method of testing hypotheses after they're offered, right? So instead of observing a bunch of swans and then drawing a general conclusion based on our observations, we just start with the general claim, right? So I'll hypothesize that all swans are white. And I'm not making any claims for its justification from observation. But what I can do is then test that claim, right, through experiment. So you might ask, well, if we don't come up with hypotheses by induction, then how do we do it? And Popper says, I don't know, that's just something about how human brains work. That's a psychological process. Maybe it's just inspiration, right? And sure, interesting subject, but it's something for psychologists to study. And it's actually not something that we in philosophy of science should worry about, right? It's not a rational process. There's no logic behind it. So let's just skip that part and start with the general hypothesis. And from there, we can move and analyze it and test it deductively. So how do we do that? So you start with your hypothesis, theory, etc., and you then deduce some conclusions from that, right? So we'll have to move. So one, right, if my theory was that all swans are white, one conclusion I could draw from that is the next swan I observe will be white, right? And then I can go out and test that. And so that's one thing we can do, right? But before we get to sort of like the point of this, there's a few things we can do with those conclusions. Now, most theories are going to be more complex than all swans are white, right? You might have Newtonian mechanics, right, which has a lot of different laws that govern the motions of bodies and gravitational fields and things like that. So when you've got your theory and you've got several different sort of laws involved, right, you can derive various conclusions from it about the way, if we're talking about Newtonian mechanics, about the way different objects will behave in different situations when they're under different forces. And first of all, you can make sure that all those conclusions are logically consistent, right? So what you don't want is a theory that says if I drop my phone, it will fall down and it will fall up, right? That's contradictory. That means there's serious problems with your theory, right? So that's one sort of test. Just make sure your theory is consistent. Do that by deducing conclusions from it. You can also deduce conclusions, right? It will help you determine if you're actually dealing with a scientific theory or something else, something like metaphysics or something, right? So for a good scientific theory, the conclusion, it should produce conclusions that can be tested by observation, right? So if your theory is something like if one of the conclusions of your theory is that like all tabby cats will be beautiful, or something like that, something that's not really testable by observation, or even more like we'll see later, a lot of these philosophers and scientists like to make fun of Heidegger, who was a German philosopher. So they grabbed this quote from one of his books that says, he says, "The nothing nothings," right? And this is supposed to mean something, I think, if you know Heidegger a little better. But a lot of later philosophers of science looked at it and said, how the heck could I observe? How could I test and verify whether that's true? That the nothing nothings, right? How am I going to observe that, right? So if your scientific theory, if the conclusions you derive are things like the nothing nothings, then maybe there's some problem, or at least maybe it's not a scientific theory, right? You want conclusions that can be observed and tested to see if they're true or false. Another thing you can do, right? You can deduce, and again, none of this requires induction at all. This is just using deductive modus ponens, right? All the familiar rules of deduction. You can compare the conclusions that you get with competing theories, right? And see if your theory actually says anything new, right? If all of the observable consequences of your theory are the same as the old theory, then maybe you haven't actually come up with a new theory, right? But if they conflict, now this is where it gets interesting, right? So now you have a new theory, and it says that, right, when you refract light through a prism, you'll see an oblong image. And if the old theory says when you reflect light or the sun through a prism, you'll get a round image, now we have the potential, right, to decide which theory is false, right? And this is number 4. You can test your conclusion with an experiment and see if it's false, right? So if my theory says sun refracted through a prism will produce a round image, and then Newton goes, right, and tests it, and he gets an oblong image, that means that the old theory was false, right? All deduction, right? So that's modus tollens, right? If A, then B, not B, therefore not A. So we'll get into this a little more. That's another rule, like modus ponens is another one of those deductive rules of logic. Okay, so falsification is this last thing, right? This is Popper's big innovation. It says science progresses by modus tollens. So again, we have Newton, right? So he says, if light is made up of just one kind of ray, then sunlight bent through a prism should produce a round image. But we find that when the sun goes through a prism, it actually creates a different image, an oblong one, right? A not round one. Therefore, we can conclude that light isn't made up of just one kind of ray. And we can formalize this into logical form, right? So if P, then Q. So if light is one kind of ray, then sun will produce round image. Not Q, sun does not produce round image. Therefore, not P. Therefore, light is not just one kind of ray. And this rule, where you go P then Q, not P, this rule is called modus tollens. Right? Maybe if you haven't taken logic, a simpler version, right? So if it rains, then the streets will get wet, right? I look outside and the streets are not wet, therefore I conclude it didn't rain. Right? So it's a pretty common form of reasoning, and it's deductively sound. Okay, so if you have a new theory, make some prediction, and then it contradicts some prediction of the old theory, then you can do an experiment. One of them has to be wrong, right? They can't both be true. So you do the experiment, see which one turns out false, which prediction turns out false. Now, what you can't do, however, is do an experiment to see which theory is right. So what Newton did, according to Popper, he did not actually prove that light is composed of different rays that refract at different angles. So he didn't prove his theory. What he did is disprove the other theory. He proved that light isn't composed of only one kind of ray. Right? You don't confirm theories, right? Your theory is never confirmed because deductive logic just doesn't allow us to do that. That's called a fallacy. It's called affirming the consequent, right? We say if it rains, the streets are wet, and you look out and the streets are wet, you cannot actually conclude that it rained, right? There's lots of ways the streets have gotten wet. Maybe the street cleaners came through. Maybe I ran a hose. So unfortunately, there isn't a deductive way to prove a theory is true. There's only deductive ways to prove theories are false. But Popper comes up with a new term for what happens when a theory has survived a bunch of tests and sort of keeps not being falsified. And he calls that corroboration, right? So it's not quite being proven true, right? Because that can't happen deductively, but it's pretty good, right? That's the best a theory can hope for, is to be corroborated, right? So long story short, right? Popper's response to the problem of induction, he says, yeah, it's a big problem. We shouldn't do induction. He says, that's okay. We can still do science. We do it deductively by falsifying theories. And unfortunately, that means that a theory is never definitively proven true, but it can be what he calls corroborated. So again, let's look back at Zig, right? So he believed this general law, like the law of donut delectability, all donuts delicious, but it was falsified, right? He ate one horseradish donut is sufficient to falsify his theory, right? Just a deductive argument. So here's the logical form of that, right? I'm going to give you a little practice with these because, again, you'll run into them in the readings, right? So here's all donuts are delicious. Translated into logic looks like this. You got the parentheses with the X. Sometimes I put an upside down A, but different people do it different ways, so I want you to get used to both. So X in parentheses means for all X, for everything in the world, NX. If it's a donut, arrow, then DX. It's delicious. I had to use N for donut because I didn't want to use two Ds, right? So again, it means for anything whatsoever, if it's a donut, then it's delicious. That is the law of donut delectability. Now, just a little bit on the logic of this. So notice, right, I said for everything in the universe, right, for all X. So the law of donut delectability sort of applies to everything in the universe. So you could apply it to a shoe or the planet Jupiter, right? So you say, so suppose X is a shoe. Well, if the shoe is a donut, then it's delicious. But the shoe isn't a donut, right? So the law doesn't predict that it will be delicious. Same with Jupiter, but because a chocolate donut, right? If it's a donut, oh, it is a donut, then it tells us something about what will happen, and it tells us that the donut will be delicious, right? So just a little bit on the logic of these. I try to ease you into it because reading it, you sort of assume some of it. So is the law of donut delectability true? Well, it comes out true for the shoe because it's not a donut, right? So it basically doesn't make any predictions about it. Comes out true for the chocolate donut, comes out true for Jupiter. So they don't falsify it, right? So thus far, the law of donut delectability has been sort of corroborated a little bit, but only with 3 experiments, right? But now we have the horseradish donut, right? This is a problem because it satisfies the donut, right? It is a donut. And so the law of donut delectability predicts that it should be delicious, and it is not. So here we have our argument by modus tollens. We can falsify the law of donut delectability. If LDD is true, there are no non-delicious donuts. Horseradish donuts are non-delicious, therefore LDD is false. Okay, so one more example, back to Newton, right? So according to Popper, Newton was trying to do induction, right? Which was one way we described it, because he did try the experiment a few different ways, right? In different circumstances, different prisms, even different setups. So maybe he was trying to do individual observations and then draw a general conclusion. Popper says if that's what he's trying to do, he did not do it, right? Because you can't do induction, according to Popper. So he failed at that. But what Newton did succeed in was falsifying the previous theory, right? He derived a prediction of the old theory that a round image would be produced, and he did an experiment, and that prediction was not true. And so modus tollens, he refuted the old theory. But that's good. That's a big deal, right, in science, to refute an old theory. And that's progress. That's new knowledge. We know that something is not true. So that is progress. And he did something else. Newton did something else significant, and strictly speaking, it's sort of a failure, right? He failed to refute his own theory. He didn't falsify it. But it's a real good, special kind of failure, right? Because there's lots of ways you can fail to falsify a theory. You can not falsify it because you just don't get out of bed and don't do the experiment, right? Or doing a really bad experiment. But he performed a really good, really careful experiment, right? That should have falsified his theory if the theory was in fact false, right? And it didn't. So that means something. And right, so again with corroboration, right? So there's lots of that he did fail to falsify his theory, Newton, right, when his prediction came out true, but he failed to falsify a lot of theories, right? So he also failed to falsify the theory that light rays in England refract by different amounts, right? Or light rays on Tuesdays and Thursdays refract by a different amount. So then we kind of still run into the same problem of induction, right? Well, there's some sort of support when your prediction comes out true, but support for what? Support for the really general claim, or maybe support for only a very sort of like narrow claim about conditions on that day, right, in that location. And so this is where, again, Popper talks about corroboration, right? And so to corroborate a theory, right, it's not enough that it's just fails to be falsified, but it has to be a really like special kind of theory. It has to be bold, right? It has to make predictions that could be falsified, right? And you have to do an experiment designed to falsify it, and still fails to be falsified, right? So it's not just any kind of falsification is interesting, right? And not just any sort of support for your theory is interesting. Corroboration involves really bold theories that make strong predictions, and you do a good experiment that should falsify it if it was false. Right? So Newton's got a general theory, right? He's not making a claim just about England, light rays in England, or light rays on Tuesdays. So it makes more predictions. That makes it a better theory. It makes it a bolder theory. And that's why it's better, according to Popper. And one last little note, right? There's an issue that I just didn't have time to talk about in this course called the demarcation problem, where you might want to know, well, what counts as science and what doesn't, right? How come astrology isn't a science, but astronomy is? And one thing, or what Popper thinks is the right way to think about it, is that science is falsifiable and non-science, right, pseudoscience, is not. So typically, like take astrology as an example, if you read your horoscope, it's not going to really say anything that's falsifiable. It's going to say very general things, like today is a good day to try new things, right? Okay, how do you make that false, right? Okay, well, maybe you could try one new thing. You could try bungee jumping and you end up breaking your arm or something. But, right, you could easily see your astrologer saying, oh, well, we didn't mean that, right? Or, well, in the long run, it was a good thing, right, that you tried bungee jumping and broke your arm. Or actually, the new thing we were talking about was the new kind of gum that you tried that day, right? So, this is a tricky subject, right? And we can't spend enough time on it. Maybe your astrologer would have some way to respond to that, right? But anyways, this is one possible way of sort of like drawing the line between science and non-science. Science is falsifiable, non-science arguably not. Okay, and so this is sort of like leading into the next lecture, but let's go back to Zig and his horseradish donut. Now we've noticed that Zig is very stubborn, right? He really doesn't want to give up on the law of donut delectability. So just because he tries a horseradish donut and it's disgusting, is he required, right, by the laws of logic, right, by modus tollens, to give up the law of donut delectability? Well, maybe not, right? He might refuse to accept that that horseradish thing was in fact a donut, right? He may insist it was a bagel, in which case um, it doesn't satisfy the first part of the law of donut collectability, right? It's not a donut, and therefore the law of donut collectability doesn't make any prediction about its deliciousness. Or he could talk himself into thinking that it was actually delicious, right? He could deny that part of it. So here, right, Popper calls this part the empirical basis of falsification, right? Where was the donut delicious or not, right? Here you're kind of dealing with human psychology a little bit, right? So your observations are obviously filtered through your brain, through your visual system or your taste buds in the case of donuts, and it it can be a little fuzzy, right? What did we observe? We observe, especially when you're dealing with very complicated instruments and like sort of complicated interpretations. Like if you're talking about electrons, you're looking at like tracks and cloud chambers. We'll see some pictures of those later. Um, so there always is a bit of a psychological element to that part of falsification. Um, and so it's going to be sort of up to scientists whether they're willing to accept the results of an experiment. And you will find that scientists who have been working on a particular theory for their entire career, and they get one experiment where their predictions come out false, they're going to find a million ways not to accept that their theory has been falsified, right? And so they'll look high and low, and the human mind is pretty expert at finding justifications for you were right the whole time, right? So it's not quite as simple as, right? Popper admits that it's not quite as simple as it might seem, falsification, but it certainly does to him seem to be a vast improvement on seeing science as induction, which he doesn't seem to see any rational basis for whatsoever. And the next lecture, we'll talk about the do-him problem, which poses some much, much trickier problems for falsification, Popper's whole account.